Some highly intelligent raptor descendants were documented teaching their offspring to craft and use stone tools for butchering prey. Enormous, fully aquatic dinosaurs, evolved from semi-aquatic spinosaurids, used complex patterns of low-frequency sounds to communicate across entire ocean basins. Vast herds of hadrosaurs, insulated by thick coats of downy feathers, undertook seasonal migrations across newly formed Arctic plains. Colonies of tiny insect-eating alvarezsaurid dinosaurs, excavated subterranean networks that spanned several square miles featuring specialized chambers for food, storage, and raising young. Certain ceratopsian species developed glands that produced potent neurotoxins, delivered through grooved, horn-like protrusions on their elaborate frills. Number 8. The brainy jarts that basically invented science fairs. The dromaeosaurs, those feathery, sickle-clawed predators often called raptors, were already pretty smart back in the Cretaceous period. They hunted in packs, had decent-sized brains for dinosaurs, and sharp senses. When the asteroid never came, these sharp minds got even sharper. Over millions of years, in a world still dominated by reptilian giants, the pressure to outthink prey and rival predators pushed one lineage of dromaeosaur towards something remarkable. These weren't the bulky movie-style raptors, but smaller, more agile descendants perhaps from something like Sauronathalestes, or a similar gracile form. Their brains began to expand significantly. Fossil skulls from this alternate Cenozoic show progressively larger brain cases, especially in regions associated with problem-solving and social behavior. Their hands, already quite capable, evolved even greater dexterity. The famous sickle claw on the foot, while still a formidable weapon, also became a tool for manipulating objects, prying open hard-shelled prey or digging. These evolved raptors, let's call them cod carts, didn't build skyscrapers, but they did develop what could be described as a rudimentary technological culture. Evidence found in ancient riverbeds and former nesting sites includes deliberately shaped stones. Some were simple choppers and scrapers used for processing carcasses. Others were more complex, like sharpened flakes, clearly napped from larger cores, displaying an understanding of stone fracture mechanics. These tools were not just instinctive creations, where patterns and caches of unfinished tools suggest they were crafted with intent and skill, and these skills were likely taught. Imagine a Cog Raptor elder patiently showing a juvenile how to strike a flint core just right to produce a cutting edge. Their social structures became incredibly complex. They lived in extended family groups, or clans, with clear hierarchies and cooperative strategies that went far beyond simple pack hunting. Vocalizations became more nuanced, a rich language of chirps, whistles, and growls capable of conveying complex information about food sources, danger, or social status. Their feathers, already present for insulation and display, became even more elaborate, used in intricate communication rituals. Different clans even developed distinct dialects and feather display patterns, akin to regional cultures. They established semi-permanent home bases, often in sheltered rock formations or dense thickets, which they would modify by clearing areas or creating simple windbreaks. There are even tantalizing hints of symbolic behavior, arrangements of colored stones or unusual fossils found at some sites, suggesting a dawning sense of aesthetics or perhaps even ritual. They were not human, but they were undoubtedly the intellectuals of their age, constantly observing, learning, and adapting in a world that never stopped challenging them. They mapped their territories, understood seasonal changes, and tracked the migrations of their prey with astonishing accuracy, passing this knowledge down through generations. Number 7. Ocean Kings. How Spinosaur descendants became dinosaur whales. Spinosaurids, like the famous Spinosaurus itself with its crocodile-like snout and enormous sail, were already semi-aquatic fish eaters in the Cretaceous. They waded in rivers and coastal waters, snatching prey with their conical teeth and powerful claws. Without the asteroid to end their reign, some spinosaurid lineages took to the water more and more permanently. The oceans, still recovering from earlier extinction events, but rich in fish, squid, and marine reptiles, presented a vast untapped opportunity for these adaptable predators. Over tens of millions of years, these Aqua-Spines underwent a dramatic transformation. Their hind limbs, less useful in water, gradually reduced in size, becoming small internal vestiges, much like those in modern whales. Their powerful tails, already flattened side to side in their ancestors, developed broad flukes, providing the main propulsive force for swimming. The forelimbs initially used for grasping prey and perhaps some paddling evolved into steerable flippers, their clawed fingers becoming encased in a web of skin and connective tissue. Their bodies became highly streamlined, losing the prominent dorsal sail of their ancestors, which would have created too much drag. Instead, they developed a smooth, blubbery layer beneath their skin for insulation in cooler waters and buoyancy, their scales becoming tiny and smooth or even lost altogether in some species. Their heads also adapted for a fully marine existence. Nostrils migrated towards the top of the skull, allowing them to breathe with minimal effort while mostly submerged, similar to a whale's blowhole. Their eyes became larger, adapted for seeing in the dimmer light of deeper waters. The long, narrow snouts remained, still packed with pressure-sensitive pits that helped them detect the movements of fish and other prey in murky water, or even when visibility was zero. Some species of Aqua-Spines grew to enormous sizes, rivaling the largest baleen whales of our timeline. These giants became filter feeders, evolving bristle-like structures from modified teeth or dermal growths inside their mouths to strain krill like crustaceans and small fish from the water. Other lineages remained active, hunters developing impressive speed and agility to chase down large fish, plesiosaurs, and even other marine dinosaurs. One of the most fascinating developments was their communication. Sound travels exceptionally well underwater, and the Aqua-Spines evolved the ability to produce and perceive a wide range of low-frequency sounds. These rumbles and moans, generated in specialized air sacs connected to their respiratory system, could travel for hundreds, perhaps thousands of miles to the ocean depths. They used these calls for long-distance communication, for coordinating hunts among dispersed group members, for attracting mates, and for navigating through the vast featureless expanses of the open ocean. Their brains, particularly the auditory processing centers, were highly developed. The deep oceans of this alternate Earth echoed with the complex songs of these dinosaurian marine titans. Number 6. Arctic hadrosaurs, duckbills that wore feather parkas. Hadrosaurs, the duck-billed dinosaurs, were incredibly successful herbivores in the late Cretaceous. They roamed in large herds, munching on vegetation with their complex batteries of grinding teeth. As the Earth continued its slow cooling trend into the alternate Cenozoic, without the asteroid's abrupt climate catastrophe, these adaptable dinosaurs found new frontiers opening up in the higher latitudes. Lush temperate forests gradually gave way to taiga, and eventually tundra-like environments in the far north and south, and the hadrosaurs followed. One group of hadrosaurs, perhaps evolving from forms like Edmontosaurus, became specialists in these colder climes. These Cryo-Ducks developed remarkable adaptations to survive freezing temperatures and long, dark winters. The most striking of these was their insulation. While many dinosaurs had some form of feathery covering, the Cryo-Ducks evolved an incredibly thick, dense coat of downy protofeathers, overlaid with longer, coarser, weather-resistant feathers. This plumage, sometimes several inches thick, provided insulation comparable to that of Arctic mammals in our timeline. Fossilized skin impressions clearly show these complex feather structures. Young Cryo-Ducks were born with a particularly dense layer of down, keeping them warm while they grew. Their physiology also changed. They likely developed a higher metabolic rate than their warmer climate cousins to generate more body heat. Layers of subcutaneous fat provided additional insulation and energy reserves to get them through lean winter months. Their broad, duck-like bills, already efficient for cropping vegetation, became even more robust, suited for stripping bark from hardy conifers, digging up frozen roots and tubers, or browsing on tough, low-growing Arctic shrubs. Their dental batteries remained highly effective, capable of grinding down even the most fibrous plant matter. Some species developed wider feet, almost like snowshoes, to help them move across deep snow. Cryo-Ducks were highly migratory. They undertook vast seasonal journeys following the retreating snows northward in the spring to feed on the brief but abundant summer vegetation of the Arctic plains, and then heading south again as winter approached. Their herds numbered in the thousands, a moving tide of feathered giants across the cold landscapes. Their complex head crests and nasal passages, characteristic of many hadrosaurs, were likely still used for display and communication, perhaps producing booming calls that echoed across the frozen wilderness, helping to keep the massive herds together during blizzards or in the dim light of the polar twilight. These calls might have also been adapted to resonate differently in cold, dense air, finding fossilized nesting grounds of cryo-ducks in what were once polar regions complete with eggshell fragments, showing adaptations for cold, paints a vivid picture of dinosaurian life thriving at the icy ends of the Earth. Number 5. The tiny tunnel terrors. Alvarezsaurid beneath your feet. Alvarezsaurids were small, odd-looking theropod dinosaurs from the Cretaceous period, known for their incredibly short but powerful arms, each ending in a single robust claw, and long, slender legs. They were likely specialized insectivores, using that strong claw to break into termite mounds or dig for grubs. In a world without an asteroid resetting the evolutionary clock, these diminutive diggers took their specialization to an extreme, becoming the masters of the subterranean realm. These evolved alvarezsaurids, let's call them terra miners, became even smaller than many of their ancestors, some species no larger than a rat. Their single shovel-like claw on each forelimb became proportionally enormous, a perfect digging tool. Their hind limbs remained long and strong, not for running across open ground, but for bracing themselves within tunnels and rapidly kicking excavated soil backwards. Their bodies became compact and tubular, ideal for navigating narrow burrows. Their skulls were robust, and their snouts often spade-shaped, also aiding in digging. Eyes were typically small, as vision is less important underground, but their senses of smell and touch, particularly through sensitive whiskers or bristle-like feathers around the snout, became exceptionally acute. They used these senses to locate insect nests, roots and tubers, and to navigate their complex tunnel systems. The most incredible aspect of the terra miners was their social structure. They lived in vast, interconnected underground colonies that could stretch for miles, housing thousands, even tens of thousands of individuals. These were not just simple burrows, but intricate networks with specialized chambers, large nurseries for communal care of the young, food storage galleries packed with dried insects or hoarded tubers, ventilation shafts to ensure air circulation, and even latrine chambers to maintain hygiene within the colony. Different castes or roles may have emerged within these societies, though direct fossil evidence for this is subtle. Some individuals might have been primary diggers, others foragers, and yet others dedicated to raising the young, similar to social insects or naked mole rats. Their primary food source remained insects, ants, termites, beetle larvae, which were abundant. Their digging prowess allowed them to access insect colonies deep underground that were unavailable to other predators. They likely communicated through a combination of scent marking within their tunnels and subtle vibrations or low-frequency thumps that could travel through the soil. Their skin was probably mostly bare or covered in very short, velvety fur, like feathers to reduce friction in tunnels, though some species that foraged more on the surface might have retained more extensive feathering for insulation. Finding fossilized Terra Minor cities is an archaeologist's dream in this alternate timeline, revealing a hidden world of complex dinosaurian society thriving right beneath the feet of the larger creatures that roamed the surface. These tiny dinosaurs demonstrated that success didn't always mean being big and fierce. Sometimes it meant going underground and working together. Number 4. Ceratopsian cobras, horned dinosaurs, with a venomous surprise. Ceratopsians, the horned dinosaurs, like Triceratops and Styracosaurus, were already well-defended herbivores in the late Cretaceous. Their impressive horns and massive bony frills provided excellent protection against large theropod predators. But in a world where predators continued to evolve, becoming smarter or stronger, some ceratopsian lineages developed an even more potent defense mechanism: venom. This wasn't a common trait among dinosaurs, making these venom horns particularly noteworthy. The evolution of venom in these ceratopsians likely began with specialized glands in their mouths, perhaps initially producing digestive enzymes or mild irritants. Over generations, driven by the relentless pressure of predation, these secretions became more toxic. The delivery mechanism was key. While a venomous bite was one possibility, some species developed a more unique system. Grooves appeared on their existing horns, or more commonly on newly evolved, smaller, sharp, horn-like protrusions along the edge of their elaborate frills. These venom spurs were connected to venom glands located at their base, within the thickened skin and connective tissue of the frill. When a predator attacked, attempting to bite the neck or frill, these spurs could inject a potent cocktail of toxins. The venom itself varied between species. Some venom horns produced neurotoxins that quickly incapacitated or disoriented attackers, while others had hemotoxins that caused rapid tissue damage and internal bleeding. The frills, already used for display and species recognition, took on an additional role: aposematism, or warning coloration. Bright contrasting patterns of reds, yellows, and blacks on the frills of venomous species signaled their dangerous nature to would-be predators. Fossilized skin impressions alongside these specialized frill spurs show evidence of pigment patterns consistent with such warning displays. Predators that survived an encounter with a venom horn would learn to avoid individuals with those markings. This new defense didn't mean they abandoned their old ones. Their large brow and nose horns remained formidable weapons for direct combat, and their powerful beaks could still deliver a crushing bite. Venom was an added layer of deterrence, particularly effective against predators that tried to get past the main horns to attack the vulnerable neck area. The social behavior of venom horns might have also been influenced by this adaptation. Perhaps their defensive formations were even more effective, with individuals on the periphery presenting a bristling array of venom-tipped frills. Juvenile venom horns, whose horns and frills were less developed, might have relied more heavily on the venom of the adults in the herd for protection, or perhaps they produced a milder venom from a younger age. The discovery of fossilized predators with unhealed bone damage consistent with venom-induced necrosis near venom horn tells a silent story of this potent evolutionary innovation. Number 3. Living tanks, ornithomimids that traded speed for super armor. Ornithomimids, the ostrich dinosaurs, were known for their speed and agility. Lightly built with long legs, they were the sprinters of the dinosaur world, likely relying on flight to escape predators. However, in an alternate Cenozoic where predators like the Cog Raptors, number 8, became increasingly intelligent and coordinated, or where new, larger theropods emerged, sheer speed wasn't always enough for some ornithomimide lines. One group took a drastically different evolutionary path, sacrificing their primary defense for a more robust one: heavy armor. These armored struthios evolved from a basal ornithomimid stock that perhaps lived in environments where open running space was limited or where ambush predators were common. Over millions of years, their bodies became heavier and more robust. Their light, hollow bones gradually thickened. The most significant change was the development of extensive osteoderms, bony plates embedded in their skin, covering their backs, flanks, and even their necks and tails. In early forms, these were small, isolated scutes, but in later species they fused to form large, interlocking plates, creating a near impenetrable carapace, somewhat analogous to that of an ankylosaur, but independently evolved. Some species even developed bony spikes or clubs on their tails, transforming them from fleet-footed runners into walking fortresses. Their diet likely remained omnivorous or herbivorous, but their feeding strategies might have changed. No longer able to rely on speed to chase down small animals or flee to new foraging grounds, they became slower, more deliberate browsers and grazers. Their long necks, a common ornithomimid trait, were still useful for reaching higher vegetation or spotting danger from afar. But they were now more thickly muscled and armored at the base. Their limbs became shorter and sturdier to support, their increased weight ending in broad, hoof-like claws. While they lost their top speed, they retained powerful leg muscles, which could be used to deliver devastating kicks if a predator got too close. The evolution of this armor had a profound impact on their behavior. They were likely less social than their running ancestors, perhaps living solitary lives or in small defensive groups, as large herds would be less necessary when individual defense was so high. Their feathers, if present in their ancestors, may have been reduced or lost in areas covered by armor, though some species might have retained them on their underbellies or for display on unarmored head crests. These armored struthios were a testament to the diverse evolutionary pathways available. Instead of outrunning danger, they became impervious to it, lumbering through the forests and plains, their bony armor deflecting the attacks of even the most determined carnivores. Fossil sites reveal them alongside their more gracile, speedy cousins, proving a fascinating divergence within the ornithomimid family tree. Number 2. Sky gliders, the paravians that ruled the treetops like flying squirrels. The Parav's clade includes dromaeosaurs, troodontids, and birds. Many small Cretaceous paravians, like Microraptor, already had extensive feathers on all four limbs and their tails, suggesting gliding capabilities. Without the Chicxulub impact wiping the slate clean, and with birds, Avilae, already taking to the skies with powered flight, other paravian lineages continued to explore aerial locomotion, but not necessarily full-flapping flight. Some became supreme gliders, dominating the canopies of the vast forests that flourished in the alternate Cenozoic. These canopy soarers evolved from small, arboreal ancestors. Their four-winged configuration, seen in Microraptor, was refined and enhanced. The feathers on their arms and legs became even longer and more aerodynamic, forming broad gliding surfaces. Their tails, often long and stiffened with bony rods or specialized feathers, acted as rudders for steering and stabilizers during glides. Their bodies remained lightweight, with hollow bones, but their pectoral, chest, and pelvic, hip, girdles became more robust to handle the stresses of launching and landing. Claws on both hands and feet remained sharp and recurved, perfect for gripping bark and maneuvering through branches. Some species developed a patagium, a membrane of skin stretching between limbs similar to that of modern flying squirrels or colugos, further increasing their gliding surface area. They were not just passive gliders. They were highly acrobatic. They could launch themselves from high branches, covering considerable horizontal distances to reach other trees, to escape predators, or to pounce on prey. Their eyesight was exceptionally keen, as needed for navigating complex three-dimensional environments and spotting food from afar. Their diet was varied: insects, small lizards, primitive mammals, eggs, and even fruits or nectar from the evolving flowering plants. Some larger canopy soarers became specialized predators of other arboreal creatures, including smaller gliding dinosaurs. The forests they inhabited were multi-layered, and different species of canopy soarers specialized in different strata of the canopy, reducing competition. Some were denizens of the emergent layer, making long glides between the tallest trees, while others flitted through the dense understory. Their nests were often built high in trees, well hidden among foliage. Social structures varied. Some were solitary, while others formed small family groups or loose foraging flocks. They communicated with a range of chirps, whistles, and visual displays, using their colorful plumage. These creatures were not birds in the modern sense, but a parallel lineage of feathered dinosaurs that had mastered life among the treetops through a different yet equally successful form of aerial movement. They filled a niche similar to that of squirrels and some primates in our world, adding a vibrant and dynamic layer to the forest ecosystems of this alternate Earth. Number 1. Skyscraper necks. Titanosaurs that dined on clouds. Titanosaurs were the last surviving group of long-necked sauropod dinosaurs, and some, like Argentinosaurus and Patagotitan, were the largest land animals ever known. Their sheer size was their primary defense. If the asteroid hadn't intervened, what extremes could these gentle giants have reached? One evolutionary trajectory saw certain titiansar lineages pushing the boundaries of neck length to almost unbelievable proportions, becoming specialists in high-level browsing. These Graphiditans maxima, a speculative name for this lineage, continued to evolve in environments where tall forests, perhaps dominated by giant conifers or newly evolving towering angiosperm trees, offered a rich food source far above the reach of other herbivores. The selective pressure was simple. Those individuals who could reach just a little higher gained access to untouched foliage, giving them a significant survival and reproductive advantage. Over millions of years, this led to a gradual but persistent elongation of their cervical neck vertebrae. Not only did the individual vertebrae become longer, but some lineages may have even re-evolved an increased number of neck vertebrae, reversing an earlier trend in sauropod evolution. To support such incredibly long necks, these titanosaurs developed a suite of sophisticated adaptations. Their skeletons, while massive, incorporated even more extensive air sacs, mimetization, than their Cretaceous ancestors, making the bones strong yet relatively lightweight. The musculature and ligaments of the neck were immensely powerful and complex, acting like the stays and cables of a suspension bridge. Their hearts would have been colossal pumps, capable of generating the enormous blood pressure needed to supply oxygen to a brain positioned perhaps 60 to 80 feet, or even more, above the ground. They likely had specialized valves in their carotid arteries to manage blood flow and prevent fainting when raising or lowering their heads. Their feeding apparatus also specialized. Their heads were relatively small to reduce weight at the end of that long cantilever, and their teeth were simple peg-like structures efficient for stripping leaves and tender shoots, not for heavy chewing. Like other sauropods, they would have swallowed vegetation whole, relying on gastroliths, stomach stones, and a long digestive tract to break it down. They probably browsed slowly and methodically, their long necks allowing them to sweep across a wide arc of foliage without moving their enormous bodies, conserving energy. Despite their height, they were likely still herd animals, their immense forms moving like a slow-motion forest across the landscape. The sight of a herd of Giraffatitans maxima their heads disappearing into the upper canopy or even into low-lying clouds on misty mornings, would have been one of the most awe-inspiring spectacles of this alternate world. They represented the absolute pinnacle of herbivorous gigantism, a living testament to the evolutionary potential of dinosaurs in a world they continued to dominate.